Good morning, everybody. Thank you very much for joining us for another of our Data Science Festival workshop sessions. It's actually our last session of the month, and what a month it's been, actually. We've absolutely loved running the festival this year. Obviously, we're a little bit apprehensive at the start of the month. We weren't quite sure what to expect, but it's been fantastic. We've had some great sessions across the month, and really loved having you guys with us. As I start each of these sessions, I do like to start with a thank you for our sponsors. This year we have been sponsored by Facebook, Depop, ASOS, Dataiku, Gusto, Deliveroo, Data Idols, and of course today's partners at Royal Mail. Royal Mail, they stepped up, I guess, beginning of the year to come on board as a sponsor. It was their first time sponsoring, and then obviously the pandemic hit. They were very unwavering in their support, which we really appreciated. They've got an absolutely fantastic team there. I'm sure the guys will mention, but they're normally looking for data science talent as well. So do follow up with the guys there. In terms of today's session, I'm going to ask if I could get Hugo and Louisa to turn on their cameras and microphone. We'll get you guys introduced. In terms of today's session, originally the plan was to have Fabrice, Hugo and Louisa with us. Sadly, Fabrice's father's not very well at the moment. He's not been able to join us, but Louisa and Hugo have very bravely stepped up to take over the whole show and deliver the session. So thank you both very much, and welcome along to one of our workshop sessions. How are you both this morning?
Thank you. Exciting.
Yeah, pretty good, thank you.
Perfect. These sessions are designed to be interactive, guys. So we have the Q&A feature. So any questions as we're going, please use the Q&A. The rough format for the session, we're going to start with an introduction. We're then going to move into setting up the environment before we then dive into, the guts of the workshop, the more technical aspects. So as I say, it's interactive. We do also have the Slack channel as well. So if you're struggling with anything as you're going, please do use that and see if we can all help each other out as well. So I think that's me covered everything. If you guys are ready, are we starting with you, Louisa, and going from there?
Yes, we are.
Perfect. So Hugo, I guess me and you will disappear. He's already done it. He's off. Louisa. So if you'd like to test sharing your screen, I'll just check you're all happy before I leave you to it.
See that okay?
Can indeed. So yeah, perfect. Hope you have a great session. Thank you once again, and I'll see you on the other side.
Great. Hi everyone. Thank you for coming to our workshop that we're running today. As was said, unfortunately Fab can't join us to run this workshop, so it's just going to be Hugo and I presenting our workshop on Going Postal, how to craft a cutting-edge route optimization engine. So within Royal Mail, we deliver a lot of letters and parcels, especially at the moment during the pandemic. Parcels are on the increase and everyone wants to have them delivered to their house. So it's essential that a business is able to adapt to this increased demand, which is why a vehicle routing problem on how to deliver parcels and make it more efficient is incredibly useful. So I'm going to start with an intro. And we'll talk a bit, and then we're going to go into more of the workshop and the coding, and you can see us do it. So I'll start by talking about the team that we have at Royal Mail, data science team, talk a bit more about the business case and the need for a vehicle routing solution, and then also the more technical side of how we could build a vehicle routing solution. So diversity is key with data science. We have a team of 21 from 11 different countries, 9 women, 10 men, a range of different academic backgrounds, including apprenticeships, undergrads, PhDs. And these are coming from a variety of backgrounds, so astronomy, biology, maths, computer science, so that we're able to cover a load of different techniques and come at it from different angles in order to solve the solution as best as we can. So the kind of projects we do range across the business, and seeing as it's such a big business, there are a lot of different areas that the data science could be applied and help out with making a business more efficient. So the team in the past have worked on projects such as estimating the delivery window. So is my parcel going to be delivered between like 11 a.m. and 3 p.m. or maybe 11 a.m. and 1 p.m. We also do fleet management. So for example, when is a van going to need to go into repair? Where does it need to be? Time series analysis, such as forecasting how much mail there's going to be on a specific day of the week, specific month, because it does change dramatically throughout the year. And also have applied techniques such as anomaly detection and natural language processing to help with fraud detection, for example, with people not paying for stamps and stuff like that. So the problem that we're going to be approaching today in this workshop is the parcel delivery problem. So as parcels are on the increase, a business needs to make sure that they optimize how they deliver so that everything gets done as efficiently as possible. So we have up to 1.3 billion items we deliver every year, which is up by quite a lot year on year. And as I said, especially during the pandemic. Slightly an old figure, but in 2017 to 18, we held a 52% market share, which is quite big, but also we are able to deliver all around the country to the furthest parts and everything. We deliver to over 31 million addresses 6 days a week. And there is a growing expectation for quality service in this highly competitive market with other parcel delivery services such as DPD, Hermes, Yodel. So it's important to have a good solution in order to be able to deliver parcels as well as we can. So the business goal is to utilize the resources we have currently to efficiently deliver parcels given variation in demand day on day. So delivering a high quality service, this is like about customer satisfaction, being able to predict a better time delivery window, for example. So maybe a 4-hour window to a 1-hour window, things like this. The requirements of the problem are that we have delivery offices where a van picks up its parcels, leaves from and will come back to keep the van overnight or to pick up more parcels to deliver another route. Other things that we need to consider, other constraints, are how big a fleet is. So we can't have 7 vans delivering parcels when we actually only have 5 vans available to us. And also accounting for workforce constraints such as workers can't work more than a certain number of hours a day because that would be unreasonable. So with these constraints, even though it would be useful, the algorithm and the maths tells us that the best solution has one person delivering 23 hours a day, and we also use 10 vans. If we only have 5 vans, and also it's unreasonable to ask someone to work that long in a day, we need to account for that. And the output of this tool would need to be a manifest, which both tells you which vans are taking which parcels and the order in which these parcels need to be delivered. So the problem we're going to start with today, which we call a puzzle, is an example of 50 delivery points in Edinburgh. This isn't realistic. There will be more than 50 people wanting a parcel delivered in a day within the whole of Edinburgh. But just as an example, at a smaller scale to run today for the workshop, we have an example of Edinburgh where we have 50 parcels. We have 5 vans available to us at the depot, which you can see here on the map in black. And we have a maximum time window of 4 hours. So a van needs to have left the depot, delivered all its parcels and come back within 4 hours. So the goal is to visit every delivery point only once, and also to minimize how far we travel and how long we travel for. So in this problem, we're going to simplify this and just focus on the time as our cost objective. So we're going to minimize how long in total it takes for all the vans to deliver all of the parcels. So an example of the output we're going to have could look like this. So we have 4 vans which deliver in a nice kind of flower looking arrangement, which is, as well as looking quite pretty, is also optimal in terms of minimizing for time. to an extent. And we have actually, out of the 5 vans available to us, only used 4 vans in this example solution to reduce the total time traveled. So, well, just as a bit of terminology as well, I've mentioned a few words and I hope it's made sense, but the depot is where the vans leave and come to, back to, and a puzzle is all the delivery points we need to deliver to. A route is a single, or a route or a duty is a single van and where it travels to and in what order. So we're going to now get on to some of the coding and the exciting part. So I think it's been posted in the chat, but if you could all clone the GitHub repo we've made available to you, that would be great. So I'm pretty sure it's in the chat. Yes, there it is. It should look like, sorry, I got many desktops. Here it is. There are instructions on how to clone the repo in the repo file. Oh, yes.
We've lost your screen share. I'm not sure if it's when you flick desktops, it dropped off.
Whoops, there you have. Sorry, thank you for pointing that out.
Okay.
It wasn't anything exciting. I was just showing you the web page you're probably all already at. Yes, so there are instructions on the README on how to clone it for Linux or Mac, or if you're on Windows, there's also instructions here. I hope you're all okay with that. So, okay, I'll just give you a few moments to do it. I am, as an IDE, I'm going to be using PyCharm today. So it looks something like this. Obviously use whatever you want to use. And we'll also be using Jupyter Notebook to start off with. So once you've set up the environment, I'll give you all a few minutes to do that. If you have any questions, please ask, and either Hugo can write a reply in that, or I can answer and try and help you out with it. So once you've cloned the repo as well, make sure to also create your virtual environment using the requirements file we've set up. So if you follow all these instructions in the installation of the README up until the quick start guide, you should be all set to go. I'll start setting up the Jupyter Notebook and hope that you'll have all got there soonish. So just as well, if anyone wants to contact us, our emails are up here. Feel free to, with any extra questions you have after the session. I'll tell you this again at the end, but I'm very happy to hear any feedback or interesting thoughts, or how much you enjoyed the session or anything like that. So while you're setting that up, I'll briefly talk about what a postcode looks like, because it'll be really useful for how we do the vehicle routing in our data science team. We use this a lot. For the example we've got today, we haven't used actual postcodes. We've called them postcode 1, postcode 2, postcode 3. So these are delivery points, these postcodes. But for information, this is what a postcode looks like. I'm sure you all recognize this if you live in the UK. So the first part of this area is the area. This will be the big place where you live. So this could be Edinburgh, this could be an area of London, it could be Bournemouth. Interestingly, the whole of Northern Ireland has BT as theirs, which is Belfast. So that's a fun fact for you guys, if you didn't know. The next bit is either 1 or 2 digits and can also have letters sometimes, is the district. So this is at a slightly smaller level. So within an area, you'd have, say, maybe 20 different districts, up to 20 different districts. We then have within these districts smaller areas called sectors, and then the smallest unit we use is called a unit, and this delivers to around 20 different houses. So around 20 different houses will have the same postcode. I think it goes up to 100. It varies greatly depending on what area. I'm sure if we asked you all, I doubt you'd know how many houses your postcode is delivered to, but it would vary quite a lot. Okay, I'm going to continue with the notebook now and hope you've managed to set this up okay. So firstly, we're just going to set the correct working directory for where we're working in. As you can see here, there is, this is the directory structure you will have cloned from our repo. As an explanation, so we have this Jupyter notebook that we'll have started. Oh, sorry, I didn't explain how I started the Jupyter notebook there to begin with. There is only one notebook here though, so I hope it was obvious. Obvious enough anyway. But this is DSF_main IP YNB. So on the notebook, and just as an instruction on how to start that, if you didn't know, you just type Jupyter notebook and then it will open up. We then have our data folder, which includes some images such as this one and the one above, and also an input folder, which has all the some examples of puzzles that we could run. So I've talked about Edinburgh, which has 50 parcels in, but we've also provided you with 4 others. So a 100 parcel puzzle in Cambridge, a slightly larger 137 puzzle in Edinburgh. We're going to, as we're building this workshop, we're going to work with the Edinburgh 50 puzzle. And within this directory, we have 3 different files. The parcel file has information on the postcodes that we're going to be delivering to and their coordinates. And then we also have matrices on distance, so how long it takes to get from A to B, how far it is to get from A to B, and also a time matrix on how long it takes to get from A to B. I'll show you the structure of these in a second, so it will be a bit more clear about how they look and how we're going to use them. We will be making an output folder and filling this up with the code that we write and run. And we also have our source folder, which consists of code we've written as a backbone for this workshop. And also it won't run at the moment if you try to run the main.py file, but it will, as we fill it in, by the end, we will be able to run this and have working solutions with varying parameters. So we'll work our way through this structure as we go through. So the first thing I will talk about is setting up the constraints we have. So this is the parameters file. So if we look into it here, so here, where is parameters? Here it is. So these won't all make sense yet, don't worry. If we just focus on the first few for the moment, in this parameter file, we specify what puzzle we're going to run. So we could run Edinburgh sample 50 or Edinburgh sample 137 or Cambridge sample 100. And we can set the hard constraints of the max number of vans we have, how long we want a duty to be or a single van route to be. And service time is also included, which is when you've gotten out the van, how long does it take to get to a door, deliver the parcel, or if they're not there, write a note, come back to the van. And we've set that as a quite generous 5 minutes for the moment. I know that postmen and women are often much faster than this, but for the example, we'll give them some extra time because they are very efficient. And we're also going to be starting at 10 AM because we want to. So if we now go back to the notebook, we've imported some of these just so you can see them here as well, some of these parameters that we will be using. And now we're going to, this is another class we've set up for you, which is the puzzle class, which is going to store all the information on the puzzle we're running. So we're going to import that file, that module, and what this puzzle class does, if I look back at the code, is it's got quite a few things in it. Most of it is just reading in the files from the necessary directory, which we do not need to code with you today because it's not as interesting as the fun stuff we're going to get to later. But essentially, when you initialize this, we load the data set and we set variables such as what the depot is, what it's called, what puzzle we're running, and later on we will be putting in the coordinates of where this hub is. And we'll also have more information on the puzzle constraints. So it's essentially taking the necessary parameters from parameters.py and incorporating them into a class that we can then repeatedly use later on. So here's some loading data sets, loading the puzzle CSV, the matrices, yes, and making sure we know what the depot is. So I won't worry about that too much. But if we go back to the notebook and initialize this class, just so you can see, here's our Edinburgh hub depot. This is the postcode of it, its coordinates, the maximum number of vans it has. So it has a fleet of 5 in this example. The maximum time for one van is 360. Yeah, I've told you this. So this is what the puzzle CSV looks like once we've imported it. As I said, for each postcode, we've assigned it an ID, which we're going to use throughout. Which goes from 1 to how big the puzzle is, instead of this, just to simplify things a bit. And it also has the coordinates of where they all are. I hope everyone's following along at the moment. Are there any questions at this point? Cool. Okay. I can see that someone's having some issues with IPython. I'm not exactly sure what the error could be. It's potentially what version of Python you've started your environment with. Maybe try using a different one. I think I'm using Python 3.7 at the moment. So if it could be that, that would be good. Yes, okay, great. So, okay, we were at the notebook. I hope you've had time to explore the bits I've spoken about so far. Potentially you've even gone further. Yes, so I was talking about the time matrix and how we go from the ones on this axis to the ones on this axis. Something you'll be able to see is that when you go from a postcode to a depot, it's not necessarily the same as when you go the other way around. This accounts for differences in potentially traffic is busier along one side of the road. Also, when you're making a left turn or a right turn, it takes different amounts of time depending on whether you have to wait for cars to be crossing the other direction. It also accounts for one-way streets and stuff like this. So when we're doing this, we make sure that this is accounted for and the data we have is as accurate as possible. So we're now going to explore what these matrices look like and what the data we have looks like for these 50 postcodes we have. So this is one of those Python files in the source folder you won't have to worry about, is the visualization. This is just to help us explain, so feel free to look at how we made them, but don't feel the need to. So here I am plotting the travel data distributions. So on the graph on the left is the time distribution from A to B, and on the right is the distance distribution from A to B. So we'll look at again at the map of where all these points fall. But as you can see, the mean time to get somewhere is around 15 minutes to get from another point to another point. But you can see that maybe on different sides of the city, this can take over an hour to get between 2 points. And it's possible and probable that when we do our vehicle routing solution, it won't be good to go from A to B when it takes 65 or so minutes. The distribution is slightly different with the distances. You can see it's skewed more towards distances which are closer together, which when we look at a map, you'll see there's quite a lot of points which are in the city centre of Edinburgh. So that does make sense to me anyway. And just one other thing that's interesting to look at is when we plot the distance matrix against the time matrix. So you can see that at lower distances and times, there's a quite linear relationship between how fast you can go. But as you have longer distances, the range of times it can take increases quite a lot. So this accounts for differences in traffic and everything, but it's an interesting relationship to see. So I showed this on the slide before, but this is a folium map of all the delivery points we have. So as you can see, maybe going from North Berwick to Blackburn over here would take quite a while, but there are a lot of points which are in the city centre. Yeah, so we did just have a break, but this was going to be a time for a break quickly. I guess we could do a look at some of the Q&A questions and talk through those. So would it be better to sort the postcodes first? The way we've done it, we haven't actually initialized the problem yet, which we will be coming to in a second. And you will see we do, for our initial solution before we optimize, we do some elements of this. But at the moment in the puzzle list we put in of all the delivery points, we're just really looking at the where they are at the moment. So we'll come to that in a bit. And do we account for real life traffic in our route optimization? We do, in the sense that the OSRM, the OpenStreetMaps data we've got it from, has accounted for it to a sense. But day to day, it doesn't change. So this is definitely an interesting point that would add accuracy to routing solution and help to deliver business needs of knowing maybe delivering from at 9 a.m. or 8 a.m. you have school crowds around certain areas, so you want to avoid that area, or at rush hour in other places you don't want to be traveling around 5 p.m. to deliver parcels on these busy city centre routes. So currently, to a sense, yes, but it could definitely be accounted for more on a day-to-day basis to make the puzzle solution more accurate. Cool. If there are no other questions, we're now going to move over to PyCharm and talk about initializing a route before we run the optimization part. So it's incredibly important to have a good initial solution, as you will come to see, because it really does affect the output of your optimization and help it get to a global minima as quickly as possible, rather than being too computationally expensive. And it does help cut out a lot of time. So if we go to the PyCharm, and we look at routes.py, I'll zoom in a bit on this. As you can see, there are a lot of functions here that help our code work. I'm just going to be really looking at two of them. So the first one we can see is we're going to try building our initial route at random. This is building initial solutions at random is a technique used in other machine learning and optimization techniques for data science. As we will come to see here, it's not the best one for vehicle routing problems, but let's look through the code quickly. And you can see that we use random seeds in order to be able, we randomize and shuffle the stop list of the parcels, and then we randomly allocate them to vans. I won't go through this too much, and we won't be coding this because you already have it. But if we go to main.py, we're going to run our first bit of code together in Python, which is exciting. So, oh, one other thing to mention, in order to demonstrate how the initial routes affect the solution, we're going to be using Google's OR tools package, which has a vehicle route optimization element to it. This is partly just to briefly show you a solution, and it can be used if you need a quick one in a fix, and it does work pretty well, to be honest. But I guess the point of this talk we were trying to say is that we have stakeholder requirements that these pre-made models and optimization algorithms won't necessarily account for. So this is in the OR tools sova.py file, but we won't be touching that. We're just going to look at what the output looks like. So at this point, if we run main, and we look down here, it initialized, oh, sorry, actually I missed a step, scratch that. Okay, if we look at line 31 and 32, we have the two different things that our root class can do. So one of them is building an initial solution from random, and one of them is building a solution from what the postcodes look like themselves, which I'll come to in a second. So if we start off by commenting out that line and commenting in this line, just to see how this works quickly. So we're going to start by building at random our initial solution, and then we are going to be running the OR tools Google package, which I mentioned before, which is here. So now if we run our main file and we look into our output, which we produce, so I'm just going to use Finder here. Ooh, where have I put my Finder? Here it is. Sorry if this is a bit small. Let's see if I can zoom in. Sorry, I hope, I don't know if you can see this well. There's not a lot that you need to be seeing though. If you go to the output folder and then the puzzle we just run, which is Edinburgh, the puzzle we just run, which is sample 50, and then what we're going to do is look at the maps. So the first one we're going to look at is the initial route map, which opened up on my other screen. So I'm going to show you here. So this is our initial route map, and we organized it at random. And as you can see, these routes are very random and very much not efficient. And the total time it took was 1,400 minutes, which is a long time, and we can definitely improve on that. We did use 5 vans though, and we did cover all 50 stops, which means that the route is valid, which you can kind of see here over this road marker. The other file we're going to look at is how OR tools dealt with this initial solution in order to make its own solution. So if I look at this map, we can see it has definitely optimized it. The total time for delivery, which we chose as our cost function, is now reduced to 900 minutes. And it does produce a valid route. But from setting up this workshop beforehand, I can tell you that we can definitely get better results than 900 minutes. So if we now go back to Python and we hash out this line instead. So we're now building from postcodes. Okay, and to explain this briefly, as I explained before in, sorry, flipping screens a lot, at the beginning of this notebook, we have our postcode structure like this. So what we did for this non-random sorting at the start is to sort postcodes alphanumerically. So all of these postcodes start with the same area because they're all in Edinburgh, but we then sorted by their district number, so 1 and 2 and 3, and then within them we sorted by the sectors and we sort by the units as well, the letters. So and the way that these areas are structured, these districts, these sectors, they are close together, so it will produce a better solution than at random because these postcodes postcodes are already sorted based on what their name is, based on what their postcode is. So if we run that code in main with build from postcode function instead of build at random, we're going to overwrite the maps we just made before. And here we can see that the initial routing now looks a lot neater. So if we can click on these as well if you want. So this is postcode EH10 5FT, which is now in the same van route as EH9. So EH9 and EH10 are very close together. EH11 also alphanumerically very close. Whereas if we look at the outskirts of town, we have EH47, EH55, so the higher district numbers are all being sorted into a similar van. And this initial solution is already better than the 1,400 we saw before. It's 953. And if we look at the solution that OR Tools is able to produce, it's actually minimized on the number of vans we want and has managed to produce a much reduced cost or total time of under 700 minutes using just 2 vans, which is incredibly exciting. And you can also see the hub here in black, which all routes need to come and go to, from and to. So as you can see, the red one goes out of it and comes back to it, and so does the blue one. Okay, so I think that is it for the initialization of problems. Are there any questions that have been answered? Doesn't look like there are. At this point, we can have another break, although we haven't actually had that long. Maybe Hugo, would you like to start on your part next?
Yes, I will be happy to start. Do people want to, could people please put in the chat if they want to have a little break, or should I start my part? Okay, I guess. Oh.
To be fair, this is a good point to stop, so maybe stop for just like
Yes.
a couple of minutes. Cool.
So we can come back in 10 minutes at 10 o'clock?
I don't know, what do you think?
What do you think, David?
I think we should keep it short and sweet. So yeah, maybe take a 5-minute break.
5 minutes, okay, 5 minutes.
Just to let people, there's a couple of people who said they're still setting up a few bits and pieces. So we'll give those people 5 minutes. I think there's a few people itching to get going as well. So we've ended up bang in the middle. So we'll come back at 5 to 10 and we'll get going.
Perfect.
Cheers.
Great.
Hello, are we good to start again?
We are indeed. Let me just stop sharing my screen.
Yes, thank you.
That'll be you ready to go. So if you'd like to test sharing yours, and if Louisa's lurking in the background, if she could keep a little eye on the Q&A, there is one question there, just finishing up on her talk. So that'd be helpful.
Can you see my slides?
I can indeed. It looks good. So I'll get out the way and I'll leave you to it. Have fun.
Okay, thank you. Okay, so I'm going to talk a bit about the optimization. So as Luisa mentioned, we are doing a vehicle routing problem, and it's a famous problem in the operational research literature. So it's a problem that can be written in integer linear programming form, as we can see, where we have objective functions that we try to maximize, and we have some constraints that we try to satisfy. So as an example, in our case, we can have the objective function could be, for example, to minimize the cost, which could be a combination of time and or distance. It could be a fuel. It could be the number of van. And some constraint might be, as someone has already mentioned in the chat, it could be, for example, that some van don't take more than a certain number of hours, as we don't want our driver to drive all day. Okay. So yes, so as I said, we are trying to solve the vehicle routing problem, which is a generalization of the traveling salesman problem. So the traveling salesman problem is will be, for example, a vehicle routing problem with only one van where you are trying to connect to connect the dot, and the vehicle routing problem is when you have more than one van and you need to make routes and come back to the depot. So this problem, so when we are trying to build a optimization solver, usually we tend to like to have the optimal solution, and we tend to like to be able to solve the problem in a linear time. However, as you can imagine, using exact method is infeasible for the vehicle routing problem because it's an NP-hard problem. Hence, we have to make some trade-off because we cannot, if you desire to get the optimal solution, we will have to wait a century. So we have to use some a heuristic approach, which is quite common to solve NP-hard problem, and basically a heuristic approach enables to find solutions that might not be optimal but get as close as possible to the optimal solution in a faster time. So usually we start with the initial solution, as Luisa mentioned, and then we try to modify the initial solution, and this can be tailored to our problem. So if you are doing a vehicular routing problem or a traveling salesman problem, you might have a different way to modify the initial solution, and then you check if the solution is better or not than your current best, and you replace it or you discard it. And so what is really nice with a heuristic approach is that you can add constraints that are, for example, non-linear, and would be difficult to solve using exact methods. So it's a more flexible approach. And us today we will talk about the large neighborhood search for the vehicle routing problem. And so basically, so I'm going to introduce how we modified the solution in order to explore the solution space. So given a route, we can destroy and repair the route using some a destroy operator or repair operator that are handmade to you, to your constraint, to your business needs. And it's quite nice because you can be really creative with this kind of operator. And then you evaluate, and if the repair route that you have built is better than your current base, then you accept it, and you can keep doing that until you have found a solution that you are satisfied with. And so the idea of the light neighborhood search is to explore the solution. So it's to explore the solution space of our problem, because you have some local search. So for example, here we can see on this picture. So the large neighborhood search, as you delete, so you can delete. So basically, you remove points from your routes, and you add them back in the most efficient way. And so you can remove a large. So usually you tend to remove large proportion of the delivery stops, and you jump very far in the neighborhood of the solution space. So for example, so usually we use large neighborhood search together with local search. They are complementary to each other. They aim to do different things. So for example, a local search, given that we are at this point, and given we are at this point, we would like to get as fast as possible to this point. And for example, the large neighborhood search might bring us to that point, and then we can work with a local search in order to get to the global optimum. So their work, they are complementary to each other. And today we will, I will now live code a large neighborhood search, a repair and a destroy operator. And but we will not go into more detail about the local search. Okay, so now time for some coding. Yes. So if you can go to the pie chart, please. And if you can go to the LNS class. So just to make sure, so we are given a route, and the aim is to remove some stuff from the route and add them back. So we will code for now the most obvious destroy and repair operator, but there are many nice ways of doing it. So for now, we will go to the random destroy. And so basically what we will do is we will simply remove stops randomly. We aim not to remove hubs from the solution. So we have a stop list. So a stop list is a list where we have the ID about the delivery stops and about end of the depot. So usually it tends to be depot, some delivery stop, depot, some delivery stop, depot, some delivery stop, and it means that a van goes in order of its delivery stop. So we create a new variable called stop list no hub, no depot. And so now we want to have we want to remove the hub from this list, as we don't want to remove the hub intentionally. Okay, so now we have a parameter. So we have a parameter that is called LNS destroy number, which is the number of parameter of a delivery stop we aim to remove from the current solution, and this is it's a fraction of the total number of stop, and it's an input to the function, and you can hypertune this value to your problem. So now we will select we will sample randomly this amount of indexes to remove from this list. Okay, so we use a sample and range 0 to self.num stop. Yes. And self.lns destroy NB. So now we will have a list of indexes that we want to remove from this list. And so self.stops removed. So now we want to access to keep track of those remove stop. Okay, and now I want to remove them as well from the current solution. So this is so we create a new object stop list. So now we want to add the ones that we didn't remove. Okay, if stop not in the stop removed. So now we end up with here a list of remove stops that we need to add back, and here the partial stop list that does not contain any more those delivery points. So now we have a function that is called compute insert array and update insert array. So basically, so our idea is to try to add the delivery stop at their cheapest possible position in the destroyed stop list. And so in order to do that, we need to calculate the cost of inserting a delivery stop between two stops. And so we will start coding the repair. So I hope it's clear how. So it inserts the cheapest remove stop at its cheapest position in the partial route, and this is performed until all the destroyed the removed stop list have been inserted back. Okay, so as I said, we need to calculate this matrix where we have the cost of inserting each delivery point at each possible solution. And so we call the compute insert array, and we give it the partial stop list and the stops that we have removed. We add this parameter. Okay, so now, this is a iterative process. So we perform it until all our stop. We want to add all of them back, and it's a recursive. So we put a while statement. So now we have a matrix where the row are the are the stops removed, and the column are the possible insertion. So we want to insert at the cheapest one at its cheapest position. So we calculate we get the index of this. Okay. And there might be more than one cheapest one. So we randomly select one. Okay, stop. Yes. So now we have. So we. So we. So we select the stop that we want to add back. Okay. Yes. Okay. So and now we sorry. So we also select the one in for the at the position and we add one, and so now we can remove the yes. So now we can take, so we can finally get the idea about the stops that we want to add back to the partial solution, and we can remove it from the stop leaf remove. Stop. Yes. Okay. So yes. So now we have the insert stop that we want to add, and we can finally add it back to the partial stop list. So here we can see with this line, we can see that the while loop will not keep on going, because this at one point will be empty. Yes, so we insert our insert our remove stop into the partial solution, into the partial stop list, and we need to update the update insert array, because we have added back this delivery stop, and also as the route has changed, we need to update the cost of inserting each of them. So this you can see more detailed in the code to understand what is happening, but it's quite basic. Basically, only two columns change in the update insert array, so we don't need to recompute everything. Just need to alter those two columns, and finally we set the new stop list to the partial stop list once they have after the while loop. Then yes, all stop have been added back. So this is a possible way to do the repair. So here it's we can see that there is quite a problem, is that we will tend to delay when we add the hard delivery stops, because we always add the cheapest. So we might yes, we might leave out the really difficult one towards the end, and this might not be the best approach to do it, but it's an approach, and there are other approaches in the literature, and you can be creative, and this is quite nice with this repair and destroyed. And I have also added another repair, which is a random repair. So basically it selects randomly a remove stop, and it add it at its cheapest position. So here we add the cheapest remove stop at its cheapest position. Here we add, in the random repair, we add a random remove stop at its cheapest position. So yes, so there are many ways to do it, and so it's quite nice. And now we see that we have both, we have two repair operator, and so you can you can in the literature there is something called adaptive large neighborhood search, which basically works with many repair operator and destroy operator to optimize when to use, because it might be good to it might be good to use a combination of the two. So you can, for example, say, okay, 50% of the time I use the greedy repair, 50% of the time I use the random repair, but the adaptive large neighborhood search tend to do it in a more intelligent way, where the chance of using one over the other evolve through the iteration according to their performance. And I am sure some people can be even more creative and use reinforcement machine learning for this kind of problem. So yes, so it's really nice and really interesting, and many things to be done. And you can also yes, so really a lot of nice things to be done with this operator. And now Luisa will continue with another very exciting module of the optimizer. So I hope.
Hi, there are some questions about
Yes.
the destroy and repair if you wanted to take them.
Yes. Okay. Oh, sorry for zoom in. I will push the code now so people can access the so that people can access. Give me one moment. Yes. Yes. So it should be accessible to everyone, the lines of code I have used. I hope I didn't make any mistake, because yes. Thank you, Luisa, for you already done it. Yes. So the random destroy remove a fixed number of stop. Yes. But it destroys them not based on anything. So, for example, intuitive way would be to say, let's remove the most expensive delivery stop, because there might be badly placed into the route of the postie. But yes, so now we just remove them randomly. But there is more advanced things to do. So to which van is the remove stop added back when repairing the route? So it's added back to the van to its cheapest position. So it can be to any van, just at its cheapest position. And we had a +1 because the route starts with the depot. So we always want, we had a +1. So yes, so yes. Yes, so Yes. Do you still want to see the random? I have pushed the random destroyed, so you might access it if you want. And Luisa has put it to the chat. So I hope you can have it. Yes. So if you have any more questions, please. Okay, then the floor is to Luisa to continue.
Hi again, everyone. So now that we've got the LNS class written, so it can do destroy and repair, we're now going to code the bit that wraps around this, that does the iterative process of destroying and repairing, seeing if the route is better or not, destroying and repairing, so that we will hopefully get to a global minima. So I'm just going to share my screen. I hope you can all see this. So I pulled the code, so I've now got Hugo's stuff here, and I hope you all have too, because if you haven't coded along, we'll need this for this next part. So if I go to the PowerPoint, which I've now lost. Ah, here we are. Okay, so the method we're going to use to do this optimization is simulated annealing. I'm sure some of you might be familiar with this, but I'm just going to quickly explain how it works. So within, we're going to run many iterations of simulated annealing, and we set in the params file. For the moment, it's going to be 100, but if you want to add more iterations to make sure that you're potentially reaching a better solution, that could also be done. But this process of simulated annealing happens inside every iteration of this. So simulated annealing is based off the metal process of annealing, which I can't say I know a lot about, so I won't focus on that for now. But what it does is it involves a temperature, which at the start of your optimization will be quite high. And as we go through, the temperature will decrease and decrease and decrease as the cost function gets better and better. So here is some pseudocode of how this works. So within the loop, we will have done the Hugo's repair and destroy method to create a new route. And this new route is called output. So, what the input is the route that was put into the destroy and repair. The output is the new route we are getting back. And we also have another route, which is the best route, which from all the iterations is the best route we've come across yet in terms of our cost function. So what we do is we update the temperature. This is based on the old current temperature of the previous iteration, and it would be updated as a function of the routes we have. We then go on to assigning, figuring out whether the new destroy and repaired route is better than the old route we had. So if the cost of this repaired route, which is cost output, is smaller than the cost of the input route to the destroy and repair, that means we now have a better route because the cost function is being minimized in this process. So in this case, where we have a better output than previously, we set our best route to this output. And what we also do is for the next iteration, we set the input, which will go into the destroy and repair, to be the output of the previous destroy and repair that we just did. The part of this that makes it simulated annealing and prevents us from getting stuck in local optima, such as here. So we've reduced the cost function and we're here. And we're now, in order to get over this local minima, we're going to need to something else. And that's what this else if statement does. So we create a probability, we calculate a probability that is based off the costs we have of the input to the repair process and the output to the repair process. And the way this function works is as the temperature decreases over time, with our optimization getting better and better in return in respect to the cost function. As the temperature gets smaller and smaller, the probability of this probability increases. This probability decreases. So this statement, but at the beginning when we have a high cost function, still the probability this probability is high. And what this means is that at the start, there's a higher chance that we'll be able to jump out of this local minima. So this is what we're doing here when even if the output is worse than the input, we still set the input for the next iteration to be this new repaired one, which does not have as good a cost, which means that instead of just getting stuck down here, we have one which has a worse cost with our objective function, and it will be able to jump out and potentially optimize to a better one and hopefully reach the global minimum. So this is the background on simulated annealing. We're now going to put this into PyCharm, which we have. So let me end this slideshow and return back to PyCharm. So in order to show that this code is working, you're going to have all of Hugo's code, which I've pulled here, as I said. I hope you can all see my screen okay. I can zoom in more if necessary. So now we are going to be going from the lns.py file to the vrpsolver.py, so vehicle routing solver. Let me zoom in on this. So some of the functions here have been given already, and we're going to fill them in now. So the first thing we're going to do, this is our main iterative process, is this function run vrpsolver. So as this has random probabilities associated with it, we first set a seed. I've created a recording performance data frame that uses this function that will apply throughout to be able to track certain properties and parameters as we go through. Okay, so first of all, we need to initialize the simulated annealing algorithm. And the first thing we do, so the thing we feed into this is the puzzle we're using, the puzzle class, and the initial route that we created before, which we're doing alphanumerically at the moment instead of randomly. So we set best route is equal to init route. And also we set the current route to the init route. Okay. And the other thing we need to do now is set the starting simulated annealing temperature. And this is a function, which we will write in a second, which we'll write now actually, which is up here, called simulated annealing initialization temperature. So this function is going to be a single line, and we're going to return a temperature that is based on flipping the simulated annealing thing we had before. So this probability. So we're going to swap this all around so that we can access the temperature. Okay, so what we have here is we're going to just go straight to returning the answer here. So we return 1 takeaway, and then we use the params file, and in the params file we specified a simulated annealing control temperature, which I'll explain in a second. And we multiply this by the current cost, which we put into this function, and we divide this by the logarithm of 0.5. And I'm not going to do the maths for you now, but essentially what this does is you're finding a temperature that means that you have a 0.5 chance of accepting a worse solution based on the fact that you allow a simulated annealing temperature that is the control temperature above the best. So I hope that kind of makes sense. I think you potentially just have to work through it yourself from doing this, but hopefully this will make sense to you. But essentially this just sets an initial temperature that means that we can get out of a local minima quite fast at the beginning. So this is going to be one of the highest temperatures we're going to reach during this process. So we're going to use this function at initialization here and have the, nope, not that. We're going to have the simulated annealing temperature is going to be equal to our function, and the cost that we're going to feed into this function to set the initial temperature is the current route, and an attribute of that is the total time. And as I said, we're going to use the total time as our cost objective. So we have now initialized our function, our algorithm, which is nice. Then what we're going to do is we're going to scroll down here to the simulated annealing part, which we're going to fill in. So this is the while loop, and we have a counter to track what iteration we're on, and also in parameters, the parameters file, we set what we want our maximum iteration to be, which, if I remember correctly, is 100. Nope. Yes, it is 100. Okay, and then we can, you know how a counter works. Okay, so the first step is to run the destroy and repair that Hugo did. So we feed in all these variables. We feed in the current route we have, which is currently just the initial route, and the other things necessary to run it. And we run this class, and that is there. So after we've run the LNS, we're going to ignore the extra constraints. We'll come to that in a bit. We're going to do the simulated annealing part. So this is the equation or the algorithm I was showing you before. So we have, if this repaired route that's gone through destroy and repair and the total time of this, it's repaired route, isn't it? Not repaired route. If the total time of this is less than the best route total time, then what we're going to do is we're going to set the best route to the repaired route. And we're also going to set the current route. So this is what's going to be fed into the next repair destroy at the next iteration. This is what we're going to feed in. We're going to set the current route is also going to be equal to the repaired route. The other thing we're going to do now is, seeing as we have a new best route, we're going to update the simulated annealing temperature using the function we created before. So let's copy that in. And we're still going to be using the current route to do this, because that's what we're going to be using at the next iteration. So, and the part of this that makes it simulated annealing was that elif statement, so else if statement. So if we have, so here we need a function that determines the random chance of accepting a solution if it's not better than the best route. So if we scroll up here to this function, random chance of accepting. So this is the probability of accepting a repaired route, even if it's not better than the current route we have. So here we do this. So we're going to first work out the probability. So the probability is equal to the exponential of the negative of the repaired route cost minus the current route cost, which is total time. And then what we do is we incorporate the simulated annealing temperature, which we've been working through. So that is all the variables we feed into this function. Then what we do is, if this probability is, actually the better way of putting it probably is, if, so we come up with a random number, a random uniformly distributed number between 0 and 1. And if this random number is less than the probability we just calculated, then we return true from the function, which means that we do want to accept this worst route. And if this is not true, then we return false. Okay, so it's quite a simple function. It's just working out a probability and is a random number less than this probability. So do we want to accept this? So we are going to take this function, and we are going to put it down here. So else, so here we had, if we have the best root, is the new root is better than the best root. Else, if the random chance of accepting is true, then what we do is we set the current root to be used at the next iteration it to be equal to the repaired root. Okay, I hope that makes sense. Are there any questions at the moment? Nope, it doesn't look like they are. Well, thank you, Hugo, if you've answered them already. Okay, so the next step we are going to do in this is to, where is it? Ah, yes. So the last part that we need to make a full simulated annealing algorithm and complete the loop. First of all, we can print the output of what we've done in this loop, which I've already written for you. So we can see it neatly down at the bottom here when we run it. And also we can uncomment this, which tracks the performance as we go through. So now we need to update the simulated annealing temperature for the next iteration. This is the part that partly contributes to the cooling of the temperature as we go through the algorithm. So what we do for this is we set the simulated annealing temperature is equal to a cooling temperature, cooling rate, a cooling rate, the rate that we want to cool our simulated annealing down. And then we multiply this by the current simulated annealing temperature we have. So this cooling rate needs to be less than 1. And the closer it is to 0, the quicker you will cool down your algorithm. But the higher it is, the closer it is to 1, the slower you will cool down your algorithm. And the more iterations you potentially have to run. Okay, so at this point, we can now also uncomment line 83. And we are ready to write, to run this for the first time and see what outputs it makes. So I'm hoping this works and I've typed everything in correctly. If we now go to main.py, currently we've just run the initializations and running OR tools. If we now uncomment all the rest of it that's there. Oh, oopsie daisy. If you don't know this command, I use command / on Mac. I don't know what it is for all of you. I hope you don't have to do these one by one. So the things we've added in, we're still going to run the OR tools solver before, and we're initializing with random with postcodes, alphanumeric postcodes rather than random. And this is the bit we've just coded, which is run the vehicle routing problem solver. So, and this makes some graphs for us, and this prints some stuff out, and this tells us how fast we run it. So if we all run main function now, oops, I have coded something wrong. So this is in the LNS. Hugo, do you know what needs to be changed with this? I can look back at pre-written stuff. So this is in the random destroy function. Not 100% sure at this point why we have a list index out of range. Sorry, you can't see that probably. I assume the rest of you are also having this problem if I am too. Please tell me if you're not, and then that would be useful. So there was the random destroy we changed. Okay, interesting. sorry, this is the danger of live coding. So I'm just going to copy and paste what we had before. So sorry if we're not completely sure what. Oh, nope, that did not format well. Let me try that again. Okay. Oh. Okay, let's see if this runs now, having copied and pasted it. Oh my God, okay. Nope, that's wrong. I need to tab this all in. Sorry, classic part of a data science coding day. Split tabs. Okay, one last try. Yay! Okay, so this wasn't very helpful to helping you all decode this, I guess. I can push the code I've got now to the repo if you want to pull to solve this issue if you're all having it as well. Let me just do that now. Okay. Sorry, thank you for the comments. People who said it was something to do with when we were initializing the stop list no depot. It wasn't being helpful. Okay, so I will just push this code quickly. So I'll push this one, this one, and I'm not going to push the changes I made to the notepad and make. Okay, I'll give you all a second to do that quickly, if you haven't already managed to solve it yourself. So one of the things that was output from this that we're going to look at is how VRP has, how our vehicle routing problem that we've just done and the simulated annealing has made a final route. So this is the initial route that we started with the alphanumeric, and it's at 953. And after running our optimization, we now have 3 vans and we have 685 minutes. So we have definitely optimized so far using the simulated annealing and greedy destroy and repair, which has been able to remove vans and decrease our cost function. So that was in the output folder. Okay, and the other thing we have just output is some figures for you to see. So let me open all of these and we can talk through them quickly. So the first one we'll look at is this convergence of what the cost looks like. So here we can see we ran 100 iterations and our best route is in red, and you can see that this constantly decreases and decreases because we never set it to anything else unless it's got a better cost to it. However, by doing this random probability in order to help us get out of local optima, the current route cost we had throughout each iteration does get worse sometimes, but this is what enables us to then make it get better again and decrease and decrease and decrease, so that we've gone from around 875 to under 700 minutes for our total deliveries for the day. The other interesting plot to look at is this one. We can see the range in times it takes for each of these vans to do it. And in the blue line, you can see how many vans we have. So initially, we get to a point where the range is quite varied. It ranges from when we have 5 vans, duty times that are quite high, from over 250 to around 50. But then by the time we get down to 3 vans, the difference in duty times is quite small, actually, which is nice. And this is one of those constraints that people within a business might want to account for, because you don't want to have one van that delivers 2 parcels and it takes like 10 minutes, and another van that delivers 100 parcels and it takes like 24 hours to do. A bit dramatic, but we don't want this. So we're now going to add to the algorithm we had here, and we're going to add some extra constraints. So we can remove that question mark. So the first constraint we're going to implement is rejecting a route if it goes over the maximum time we want a van to run for. So this accounts for making sure that there aren't people who are doing 8, 9, 10-hour days driving a van around. What we've set in params is we've set our max duty length to 360 minutes, so 6 hours. So the way we're going to do this is within our routes class that we've made for you, there's an attribute that checks if all the routes, all the vans have a valid duty time that is below the max that we want. So the way we access this is if the repaired route we have, and if it's got an invalid max time to the route, then what we do is we print that we are breaking, I'll print it nicely. So we'll print that we're breaking the max or breaking time constraints after repair process, repair after destroy and the other thing we're going to do is we're still going, even though we're now discounting this, we're still going to keep track of this in the recording the performance data frame that we made. So I'm going to copy that from down here because it's the same function. So the new performance data frame is going to be exactly the same as it was before. And also we're now going to break this loop with a continue. So if we go back to main and run this now, so if we look at the images we had before, I might have just written over them already. I think I have. When we looked at the different duty times we had before, there was a chance that at some points we went over 360 with the time for a single duty. However, with this, we don't allow it anymore. We can see if this happened because we did a printout down here, which you can't see because it's too small. Which it didn't appear to actually, because we would see it here otherwise. The next thing we're going to do, however, I can assure you we will see issues with it, is that we're going to, in vehicle routing problem solver again, we're now going to, as well as it breaking the max time constraints, we're also going to see if the repaired route breaks minimum time constraints for a route. So if we go into params, I think this is currently set at 0. So we're going to set it for an hour and a half at the moment. So change this to 90. So now if we run our main, we will see that there are quite a few iterations where we were breaking time constraints. So in that case, we just kept what the current route was and continued afterward, continued with it again and tried to repair it and destroy it again. This time we have a slightly more expensive route, but also we have accounted for some constraints that we've applied to it. So it's always that mix between accounting for constraints that you need to officially run it in real life and also just optimizing it and seeing what the maths outputs best. Okay, so if we look at the maps for this one, they're already updated on that. We can actually see that by setting this minimum time constraint, we haven't changed the number of vans we have. And the duty times look like this now. They'll be on average shorter because we still have more vans in place. And if we look at the map for this, you can see we have all 5 vans. I'm going to quickly take a look at the questions and answer the questions at the moment. So on each of our maps, each point is connected by a straight line. Does our approach look at the Euclidean distance or take actual roads into account? So yeah, when I was looking at the notebook before, we looked at what the matrix looked like. So this is what we're using to see how far it is between, or how long it takes to get between point A and B. So it does account for actual roads because it uses the OpenStreetMap data API, which we queried off. But yes, you're correct. In the map, we do use straight lines, but that's more just for illustration purposes and making the maps simpler. Just for this example, I guess if you were showing it to other people in the business, or if you were giving these routes to an actual delivery driver, it would be useful for them to know which roads to take and which directions to go. But that's a separate issue to this optimization problem we're covering today. But yes, it's definitely an extra step you could do. I feel like we've been going for quite a while, and this is probably a good place to stop quickly for a break. So after I turn my camera off there, I also just pushed all the code. So in case something's not running, feel free to pull it and it will work for everything up until, the time constraints we just put into the solver. So just looking at a few of the, so if we, so what we've done so far is we've done the best optimization can do without any constraints on it. We've imposed max time constraints and minimum time constraints. What we're now going to do is impose constraints on the exact number of vans we want to be in our solution. So even though this potentially will lead to slightly worse solutions, these constraints are important for various reasons. Off the top of my head, maybe the depot manager wants to make sure that all of his delivery drivers are back in the depot quicker, so that they can help with doing more activities and other bits of work that are needed there. So by having more vans, as a the potential that the overall time is bigger, but each individual person is back in a certain amount of time. And also, if you're already paying for 5 drivers, potentially you want to make use of them all. But yeah, it depends what you want to be doing. Maybe you want to be saving petrol costs by reducing vans, but maybe you want to use fewer people. Anyway, we're going to assume that we want an exact number of vans. So if we, I hope, yeah, you can all see my screen. So in this extra constraints bit, we're now going to add another if statement. And this is going to be if the repaired route and the number of vans in it is not equal to the number of max vans we specified in our puzzle, then what we want to do is the same as before. So I'm going to copy and paste this down here, but this time instead of breaking time constraints, we're breaking van number constraints. So it's quite a simple addition, but it does change how the algorithm runs quite dramatically, potentially. So what we're actually going to do, just to demonstrate how this works, is in the parameters, we're going to set the minimum duty time to 0. Because as we saw before, when we set it to 1.5 hours, we actually stayed at a consistent 5 vans in order to fulfill that. So if we run main now, and we can see that we are breaking van driver number constraints. Ooh, it's whizzing past, but when it stops. We are breaking van number constraints after destroying repair. So here we have kept 5 vans. However, when we look at the results, we seem to have quite a bad range in how many vans each are delivering to. So we have one van that only has a single stop in it, and it only takes 14 minutes to do that route, whereas we have another route which takes 226 minutes to do. So if we look at our map here, we can see that there's this single little route over here that just goes a little bit from the depot and then goes straight back again. So this is when we then have to figure out our parameters, and there are potentially other methods to do this automatically. But what we're going to do is we're going to set our max number of vans to 4 and our min duty time to 90. So hopefully this will come out with a better range of results. Yeah, okay. So here we have 4 vans. Each of them does a reasonable number of stops each. And as we're optimizing for time, if we look at the time they've done each down here, we can see that they've all fulfilled the conditions of being over 90 minutes, even if it's only just, and being below 360 minutes. So this is a viable solution, which is very nice to see. So this is all the constraints we're going to put into our simulated annealing algorithm for the moment, which is the maximum time and the minimum time, which in itself is also accounting for the different ranges in length that duties can have, that a single van can have. So looking at these plots, we make sure that the difference in time between the min and the max at most will be between 90 and 360. There will be other ways that you can accomplish this with your code, but we're not going to focus on that for today. But this is just one method of making sure that the range of duty times is not too bad, the variation in duty times. So the next thing we can try is just kind of looking at maybe a different puzzle. So if we go to our parameters, we can maybe try the Cambridge one, which has 100 parcels in it, if I remember correctly, not 1,000. Let me just double check that. Just looking at input quickly. Yeah, 100 parcels in it. And as we now have more parcels, I'm going to increase the number of vans to 6, just to try it out. I'm not quite sure exactly what's going to happen. Hopefully it produces a nice result. But we're now going to run this and see what happens. So as we could see from the first print out, we are running now the Cambridge depot with a max fleet size of 6 and a max duty time of 360, and also a minimum duty time of 90, but that's not printed. And we have 100 parcels to deliver to. So if we can see here that we're breaking time constraints quite often. And if we look here, we are all within the time constraints. Now we're going to look at the output folder for Cambridge and look at the maps we've produced. So the initial route, and the final route, it's opened on my other screen, which is unhelpful. So this is the initial route for Cambridge. We can see we've got city centre and outwards one, more rural areas, and we have a total time of 1,600 minutes. And when we look at the final route, we have reduced the total time of our cost from 1,600 to 1,300-ish. We still have a valid route and we're covering everything. And here we can see that we have some vans that are more dedicated to the rural areas, and we have some vans that are dedicated to the more city centre areas, which is an interesting outcome. And then we have some like this light pink one that go to a few different areas. So as I mentioned at the beginning, we've supplied you with a few different puzzles, so feel free to muck around with this yourself, change the parameters. When I was playing around with it before in the VRP solver, I was just commenting out these different constraints to see what happened. So if I get rid of the number of max vans, for example, and set the potential max number of vans in Cambridge to 9, you can see what happens. We're breaking a lot of time constraints. I'm not sure whether that's at the max or the minimum, probably the minimum. But if we look at our solution now, it has actually decided that 9 is still the best, which is interesting. But if we set our minimum duty time to 0, yeah, you can see it's not breaking the time constraints as often anymore, and it's actually improving on the iterations. If we now look at this map, it's decided that the optimum number of vans is 4. So yes, it does seem that by setting a minimum duty time of 90, it also prevents the van number from decreasing, which makes sense when you think unless a van has suddenly gone from it's more difficult to get rid of a van when you have a minimum duty time. So yeah, 4 vans seems to be a good solution. And if we look at the results, they seem to be quite evenly matched in range. And by looking at the box plot for this, I'm having 2 screens, sorry. We can see at what point it decreased and how the range changed with each of these van decreases. And the other interesting one to see is how our convergence changed throughout, which is quite nice too. So yeah, this is the majority of the coding we had today, actually all of the coding. I will push these final changes now. You can change the params for yourself. I'll just push this one. Okay, so I'll look at, let me just check the chat quickly and see if there's any other stuff. Yeah, okay, I think that's the majority of this. I'm now going to just sum everything up quickly, and then we can see if there's any other questions. So start sending them in now, and then I can have a look at them in a bit. So just to sum up what we've gone through today, we've looked at the data we had. We've acquired it from OpenStreetMaps, so all the distance and time matrices we had use accurate real-life data rather than just Euclidean distances and times to get from there using those kind of measurements. We've covered initialization and seeing that random is not the best solution when you go for vehicle routing problems, but other solutions such as alphanumeric, or there are many other ones out there that could be helpful, potentially some clustering techniques. And then we go into the iterative optimization algorithm itself, where we do a global search, and we destroy and repair all of our routes and swap delivery points between them. And then the simulated annealing to see whether the new cost of our destroy and repaired route is better than the previous one we had as we went into that iteration, including reducing the simulating annealing temperature as we go, which really aids in getting to a preventing just getting to a local minimum and reaching a global minimum instead. Obviously, using more iterations than we did today would potentially find you better solutions as well. You could see when we applied constraints that often wouldn't continue with that iteration because it was breaking the constraints quite often. So yeah, there's an element of figuring out what parameters are best. Oh, and one thing I haven't actually covered is the output of this that would go into, that you'd then give to a manager at a depot in order to help do his or her direct their vans as they come out. So actually that was something I hadn't covered yet that's also in the output folder. We'll go back to Edinburgh because it's the one we had, we used originally. So if we look in solutions, we've output some pickle and numpy things so we could import them again if needed. We outputted VRP performance, control plus doesn't work for zooming in on this, apologies if you can't see. This is what we're using to plot the graphs I was showing, like the box plot and the convergence. It's just looking at what everything is every iteration. And the interesting part is this manifest we produce at the end. Let's wait for my Excel to open and see where it does open, which looks something like this. So let me just zoom in. So what we have is different vans. So we have 1, 2, 3, 4 vans in this final solution we ran on Edinburgh. And within each of these vans, it goes from the depot and back to the depot. So if we just look at van 1 here, went too far. So we go from the depot, using van 1, we go to postcode 3, then 41, then 42, then 22, then 50. And you can see the order of the stops we're going in. So the depot is always counted as stop number 0, and then 1, 2, 3, 4, 5, 6, 7, 8. These other columns, delta distance, is using the travel matrices to see what the distance is between postcode 3 and postcode 41, for example. The cumulative distance traveled by that van is covered here. So that van covered a total of 24.5 kilometers by the end, or 0.6 kilometers if you're rounding. And then this is the same, but with the time measurement instead of distance. And here you can see, say we started our delivery routes at 10 o'clock, this one would be back by 11:31, and this one would be back by 11:43. So these kind of outputs that you'd give directly to someone who's managing the logistics of these, this kind of stuff is very useful for helping them run on the actual day when these deliveries need to be done. So you can have a flick through these as well and see them too. And you can see that van 4 had a lot of deliveries here, despite having a total end time of, which is nice. Yeah, so, sorry, 1 second. Yes, back to the presentation. So this is producing a recommendation. You could also, as well as just producing a CSV, maybe you could produce a dashboard so it's more interactive. The depot manager can be like, oh, I've only got 4 vans today. What do I do now? And like suddenly they have 6 vans the next day. Be like, oh, maybe we can use this time. Or we have a lot of parcel and letter sorting to do at the depot. We need people back quickly. So let's try and reduce the max duty times, things like this. So yes, and we've accounted for other constraints that a depot manager might want to put on you, as I've described quite a few times. Just to repeat quickly, stuff like the minimum and maximum time for duty length, the range in different duty lengths within a day, and the number of vans you use, all important things. So yes, thank you very much. I'll have a look and see if there are any other questions, but yeah, if that's pretty much it, unless Hugo wants to add anything else as well. I think we've covered it.
Hey, Louisa. Yeah, if Hugo, if you want to stick your camera back on and come back at the end. I think you two guys have done an absolutely stellar job there today. There's a couple of final questions that have come in. I don't know if you just want to sort of tackle those off, and then we'll wrap things up from there, or it may be best to pick that up after. I think as we're doing that, actually, I will give you guys a final shout out, actually, because we mentioned at the start, obviously we were meant to have Fab with us today, and we'd planned all this out weeks in advance with 3 speakers, and you guys have obviously stepped up with I think 3 hours notice or something like that, with Fab not being able to be here, covered his area of the presentation and all his code as well, and you've done a really fantastic job. So very much hats off to you guys for that. So thank you very much. Just in terms of those couple of questions, is it worth picking those up, or is it best to wrap that up? And we can always follow up with other blog posts and stuff like that if it's better to follow up offline.
Could quickly look at them. So how does the manager input changes to rerun the model? I guess the way we've done it is more from a back-end place where we just edited a parameters file and changed things. But as I briefly mentioned, we could maybe make a dashboard or some front-end user interface that would make it easier for everyone to run, and then it just produces a solution for them.
About does it assume that the stop length is constant? So for now, we didn't take into account the time, of course, of the postman to go and ring at your door, give you the package and go back to the van. We didn't take this into account in our little demo today, but you can take into account quite easily by adding, for example, a constant. If you assume it takes 5 minutes to deliver a parcel, you can add it to the time in the route, for example. So quite easy to do.
Looking at the question on optimizing things at a high level, such as for profit and customer satisfaction. Yeah, what we've presented today is different from how we would apply it as a data science team at ROML. There are many more constraints. We need to cover different constraints at different places in the country. And yes, running higher level optimizations to figure out what the best parameters are is a very good idea to be able to help do this. Yes.
Julian Snowden. So are these drops not parcel? Have you tried to take into account the number of parcel total? If someone has 30 parcel, it might take a lot of room in the van. Yes, of course. So in the real world scenario, you will take into account the package, because it's the capacity of the van is not extended, is not infinity. But for now, we have assumed that we are in the example we have worked with stops. So yes, we didn't take into account, but you can take it into account. And this is quite nice with the heuristic, is that you can add all of these constraints that are a bit. You can add constraints based on your problem and the business need quite easily. Emma, well, you can use what we have coded if you don't want to use Google Word tools. Our LNS algorithm seems to be working nice. So yes.
Yeah, there are probably other packages out there. Like the Traveling Salesman Problem is a very old computer science problem that's been around for a long time. So there are definitely other packages out there that can do similar things. Yeah, this was just a demo of how to kind of build it from scratch.
So in practice, are all van driver treated as equal? Yes. So there is no.
Yeah, we've kind of interchanged the two things today, like a van is a driver. But I guess that's another constraint. Before pandemic times, you often used to have two post people in the same van who both delivered parcels, but at the moment it's just one at the time. Yes, often those two, we use those words interchangeably for this demo though.
So do you automate the optimization of parameters? So parameter, we don't really have a say in it. If every driver has to come back to the depot in 6 hours, it might be, we are constrained to the business, but some other parameter we can play with them. And so for example, in my part, when I was talking about the destroy operator, the percentage of parcel we remove, this is the parameter that you can optimize for. And
Perfect. So guys, once again, just to reiterate, I thoroughly enjoyed it. One of the slides at the very beginning did scare me a little in that I realized Hermes had 22% of the parcel delivery market. So get back to Royal Mail. I probably shouldn't be saying that out loud. Who's using Hermes? But yeah, it was absolutely fantastic presentation. I completely take my hat off to you guys. You know, giving a presentation in the first place is obviously a big step. When things change at the last minute, you know, stepping up. As I say, I'm not sure I'd have that in my locker, and you've done an absolutely fantastic job, and you've done Royal Mail proud. And just to reiterate to the people watching, you know, Royal Mail have been a fantastic partner. I know a number of the team they're working on some really interesting problems. So do follow up with those guys, and obviously thank them for it. In terms of just also wrapping up the Data Science Festival, obviously we're a very small team. Jess and Amy are behind the scenes at all of these events. They've run 24 events with 45 speakers over the last month. It's been an absolute mammoth effort from those guys, which we couldn't do without them. So obviously massive thanks to Jess and Amy. And thank you to everyone that's come along. We've had over 4,000 people come across the month. It's been absolutely fantastic. We've thoroughly enjoyed it. And we're going to have lots and lots coming up in the new year, lots of ideas on the roadmap. So hopefully we'll see you all then. But yeah, just to wrap back up, thank you very much, Louisa. Thank you very much, Hugo. And I hope you've enjoyed yourselves, and we'll see you guys soon.
Thank you for having us.
Cheers. See you later, everyone. Bye-bye.